Hello and welcome to this revision session on particle physics for AQA A-level physics. So in the first part of this revision session we're going to be looking at the constituents of the atom. So we can represent an atom of element X in the following way. Now in this notation, Z is the proton number, so it's the number of protons in the nucleus. Now an uncharged atom will have the same number of protons as it does electrons. Now in chemistry we call this the atomic number. Now A in this notation is called the nucleon number, or in chemistry it's called the atomic mass number. Now this is the total number of nucleons, so protons and neutrons in the nucleus. So we can work out our number of neutrons, the neutron number, by doing the nucleon number minus the proton number. Now this is the extent to which particle physics was covered at GCSE. Now one method of differentiating between particles is by measuring the mass. However, our issue is that the SI unit of mass, the kilogram, can be difficult to work in for particles. So instead we use the mass energy equation to derive a more workable unit for particle masses. Now the unit of mass most commonly used in particle physics is called the mega electron volt per speed of light squared, or MeV over c squared. Now MeV over c squared is not an SI unit. Now the MeV over c squared is an easy unit of mass to mathematically manipulate. However, if you wish to determine another SI unit, so for example meters or a derived unit such as hertz, it's got to be converted back to kilograms. Now our conversion factor is that 1 MeV over c squared is equal to 1.78 times 10 to the minus 30 kilograms. Now another unit of mass which is used by particle physicists is the atomic mass unit, which is the unit of particle mass used at GCSE physics. So one unified atomic mass unit is approximately the mass of one nucleon, so either a proton or a neutron. So we define this as 1/12 of the mass of an unbound neutral atom of carbon 12. Now we know that 1 U is equal to 1.661 times 10 to the minus 27 kilograms. So to convert from your non-SI units into your SI units, you've got to multiply by the conversion factor. So you've got to be able to convert from MeV over c squared into kilograms and from U into kilograms. But you've also got to be able to go the other way around. Now again, just remember before we look at this, MeV over c squared are units of mass derived from the E equals mc squared formula, whilst the simplified units of mass are used in previous topics. So for example, we would say that protons have a mass of 1 U. Now you can see here, to convert from an SI unit, your kilograms, into the non-SI units, MeV over c squared and U, you've got to divide by the conversion factor. Now another idea we've got to understand about particles is the idea of charge. Now at GCSE we stated that particles were either positively, negatively or neutrally charged. So we would say they'd have a charge of +1, -1 or 0. Now there were no units to this, it was a relative charge of the object. Now we've got to now in A-level physics express charge in terms of coulombs, the SI derived unit of charge. So we can no longer say the electron has a charge of -1 or the neutron has a charge of 0. Instead we've now got to use charges in terms of coulombs. Now 1 unit of relative charge is equal to 1.60 times 10 to the minus 19 coulombs. So the proton has a charge of +1 or plus 1.60 times 10 to the minus 19 coulombs. The electron has a charge of -1 or a charge of minus 1.60 times 10 to the minus 19 coulombs, whilst the neutron has no charge. Now you should memorize this value for your understanding moving forward. Now for particles, to find a more useful quantity than charge or mass is in fact the charge to mass ratio. Now this is called the specific charge of the particle. Now the specific charge influences the particle behavior because the specific charge details how much a particle is deflected when it is inside an electrical field. So the larger the specific charge, the greater the deflection. The smaller the specific charge, the lower the deflection. If an object has no specific charge, it will not deflect in an electrical field. And the same is also true for magnetic fields. So the larger the specific charge, the greater the deflection in a magnetic field. The smaller the specific charge, the lower the deflection in a magnetic field. And if the object has no specific specific charge, it will not deflect in the magnetic field. So how do we calculate specific charge? Now in physics, specific means per kilogram or per unit mass, so therefore specific charge is the charge divided by the mass. Now we have our charge in coulombs, our mass in kilograms, so our specific charge is coulombs per kilogram, and the specific charge of the particle indicates how much it will deflect in an electrical or magnetic field. So like we said before, the larger the specific charge of a particle, the greater the deflection of the particle in an electrical or magnetic field. But please be aware this equation is not given to you in the equation book, rather you've got to memorize it yourself. So what you would do to work out your specific charge is you work out your overall charge in coulombs and divide it by your overall mass in kilograms. Now it's important to note that as specific charge is a scalar quantity, a minus sign is not required. Now for an ion, remember that the mass includes both protons and neutrons, but you don't need to add the electron mass because it won't affect your answer to the significant figures that are given. So as ions contain neutrons, like we said before, they'll contribute to the mass but not the charge. The specific charge of an ion is much smaller than that of a charged particle. Let's now have a look at the concept of stable and unstable nuclei. Now we learned in GCSE that the atom is predominantly empty space. The radius of an atom is about 10 to the minus 12 meters, and the radius of a nucleus is about 10 to the minus 15 meters. So this means that the radius of the atom is about 10,000 times bigger than the radius of the nucleus. Now the reason why this is the case is that the electron cloud repulsion and the proton-proton repulsion means that the atoms have an appearance of being solid and the effect of being solid when they're not. So this repulsion creates this empty space which allows them to separate from each other and somewhat act like solid balls. But the question you've got to ask is, why does most of the matter in the atom exist in the nucleus, and why is this the most stable form of matter in the universe? So let's consider the nucleus of a typical atom. Now if nature only had what we call the gravitational attraction and the electromagnetic interaction, which are the ones we encounter in our day-to-day lives, a nucleus with many protons would blow itself apart, because the electromagnetic interaction, which between two protons, because they're both positive, will be repulsion, is millions of times stronger than the gravitational interaction attracting and pulling them together. So basically electromagnetism is a much stronger interaction than gravity, so therefore in theory the nucleus should blow itself apart. Now this is still true even though the neutrons don't contribute to the electromagnetic force, only the protons do. So there has to be another force that provides an attraction even stronger than the electrical repulsion of the electromagnetic force. So this force is called the strong nuclear force. Now the strong nuclear force has the following properties. It's got about a range of 3 to 4 femtometers. Now femtometer means 10 to the minus 15 meters. Now this range is about the same as the diameter of a small nucleus. Now it's an attractive force from about 3 to 4 femtometers down to about 0.5 femtometers. Its separation smaller than this, it's a repulsive force, so it prevents neutrons and protons from pushing into each other any further. Now finally, the strong force has these properties due to the properties of the strong force boson, its exchange particle, the gluon. Now if we look at this particular graph here, this graph shows the stable and unstable nuclei as a function of protons against the number of neutrons. Now you'll see here that the black dots are the stable nuclei, the red dots represent the nuclei that exist for millions of years before they decay, and the light blue dots represent the nuclei with a lifetime shorter than 1 second. So you can see our stable and nearly stable nuclei form a narrow band in this graph in the middle. Now you'll notice that for small stable nuclei the number of protons equals the number of neutrons, whilst for a large stable nuclei the number of neutrons is much greater than the number of protons. So why is this the case? Well, in the nucleus, the electromagnetic force only acts between charged particles, protons, whilst the strong interaction acts between all nucleons, both protons and neutrons. Now if the electromagnetic and strong forces are very closely balanced, a nucleus will be unstable, so it will make the nucleus susceptible to radioactive or nuclear decay. So when the strong force is much larger than the electromagnetic force, a nucleus will be very stable and will not decay at any point. Whilst if the electromagnetic force was stronger than the strong interaction, well then the nucleus could never possibly form, because it would just be repelled and would blow itself apart. So this reason is why there are some stable nuclei in the universe and some unstable nuclei in the universe and some nuclei configurations that just never form. Now, for small nuclei, we can get a configuration where the strong interaction is much larger than the electromagnetic interaction when the number of neutrons equals the number of protons. Because you'll notice here that all the nucleons contribute to the strong interaction is larger than the electromagnetic interaction, and only the protons interact via the electromagnetic interaction, so having the same number of protons and neutrons will give a much larger strong interaction than electromagnetic. However, because the strong interaction only acts over a particular range, to produce stability for large nuclei, where the strong interaction is much larger than electromagnetic, well, we've got to increase our number of neutrons, because the strong force doesn't cover the entire nucleus. So for a large nucleus, if the proton number equaled the neutron number, then the electromagnetic force would equal the strong force, and therefore it would be unstable. So what we've got to do is, to produce this stability, we've got to add more neutrons, which will only interact via the strong interaction and not the electromagnetic interaction, so it will then ensure that the strong interaction is much larger than the electromagnetic. Now eventually though, this is only a bit of a short-term fix, because eventually if the diameter of the nucleus is just so much larger than the strong interaction range, there'll not be a large enough strong interaction produced across the nucleus to make it larger than the electromagnetic interaction. So this means that the size of the nucleus can only really be approximately the size of the strong force interaction, which is why the nucleus is so small in the atom. So let's just summarize these ideas. When the strong interaction is much larger than the electromagnetic interaction, you have a stable nucleus. When the strong interaction is approximately the same size as the electromagnetic interaction, the nucleus is unstable, whilst if the electromagnetic interaction was greater than the strong interaction, the nucleus doesn't form. So the strong nuclear force is much weaker than the electromagnetic force at distances significantly greater than the typical nucleus, but we don't encounter the strong interaction in our day-to-day lives. At shorter distances comparable to a nucleus, it becomes much stronger, so its attractive force is able to overcome the electromagnetic interaction between the protons. But the nucleus is not crushed to a point mass at very short distances, because this strong interaction becomes repulsive and keeps the nucleons apart. Now, so it's important to note that the strong interaction changes properties with nucleon separation, which affects the composition of the nucleus. So like we said before, the nucleus of an atom of size about 10 to the minus 15 meters doesn't really occur, as beyond that the attractive strong force interaction is much weaker than the repulsive electromagnetic interaction, so proton-proton repulsion cannot be overcome. In addition, the nucleus is not a point mass, as at extremely small distances the strong interaction switches from an attractive interaction to a repulsive interaction, so the protons and neutrons remain separate. So we can see the properties of the strong interaction with our particular graph here. So at distances larger than 4 times 10 to the minus 15 meters, the strong interaction does not exist, which is why nuclei can't be much larger than 5 times 10 to the minus 15 meters, because there's not enough strong interaction to overcome the electromagnetic interaction, which is repulsive. Now between 1 and 4 femtometers, or 10 to the minus 15 meters, the strong interaction is strongly attractive. This makes the nucleons stick together and stable nuclei form with diameters of this size, and smaller than 0.5 femtometers, the strong interaction becomes repulsive to ensure the nucleons don't crush to point masses and exist as neutrons and protons. So it's very important at how this works. So to summarize this, at distances less than about 1 femtometers, the nucleus can't form because the strong interaction is repulsive, so it stops the nucleus being crushed. At distances greater than 3 femtometers, nuclei can't form because the strong interaction is 0, so it stops the nucleus being too large, whilst in between here the nucleus can form because the strong interaction is greater than the electromagnetic interaction, so we've got our attractive strong interaction holding our nucleus together. So let's now have a look at particles, antiparticles and photons. So Albert Einstein stated that light was emitted in discrete packets or particles called photons, and you can work out the energy of one photon with our equation of the E is equal to Planck's constant times by the frequency in Hertz. Now Planck's constant is 6.63 times 10 to the minus 34 joule seconds. Now this is one of the most fundamental equations in quantum mechanics. So Planck's constant is one of the most important values in physics. It's proportionality constant between the energy of one photon and its frequency. Now, because it's a small value, this indicates why quantum mechanical properties are only evident on the subatomic scale. Now, this equation indicates to us that electromagnetic radiation is not continuous, but rather comes in discrete packets or chunks. So this equation indicates to us that electromagnetic radiation is not a wave, rather it is a particle. It also shows us that as the frequency of a photon increases, the energy of the photon also increases. Now, as we said before, due to Planck's constant being an extremely small number, photon energy in joules will be a very small value. So as a result, particle physicists use another unit for energy, the electron volt. Now, 1 eV is equal to 1.6 times 10 to the minus 19 joules. Now, you could be given a value of photon energy in electron volts and asked to work out the frequency. So to do this, you've got to convert it back into the SI derived unit, which is the joule, okay, and then you work out your value. Now, you can work this the link out, because we know frequency is equal to wave speed over wavelength. So therefore, the photon energy is equal to Planck's constant times by wave speed over wavelength, which you can write as E is equal to hc over lambda, where c is the speed of the electromagnetic wave. Now, this equation is probably the more common form of the equation because it's easier to measure wave speed compared to frequency. Now, this equation does indicate to us that as the wavelength of a photon increases, the energy of a photon decreases. So this theory states to us that the different parts of the electromagnetic spectrum are actually all different types of photons. So the larger the frequency of the photon, the more energy stored in the photon, the more energetic the region of the electromagnetic spectrum. So we can say that the smaller the wavelength, the more energy stored in the photon, the more energetic region of our spectrum, as you can see here. So the different parts of the electromagnetic spectrum contain the same photons, just with different frequencies. So gamma ray photons contain more energy per photon compared to radio wave photons. And you can see here an example of how to work out photon energy. So you say E equals hf. H is a constant. We know the value of F from the equation. We can work out our value in joules. Same idea if you've been given the wavelength of the photon. So 590 nanometers. We use our equation E equals hc over lambda. H and c are constants. We've got lambda in the question. We can work out the energy in joules. And finally, we can also convert the value from EV into joules by working out our value in EV and then multiplying by 1.6 times 10 to the minus 19 to get our value out in joules. Now, a laser beam is an intense beam of light, but we can also consider laser beams in terms of photons. So a laser beam consists of photons of the same energy. So laser beams are very large streams of photons being emitted, and we say that the photons in the laser beams are coherent with each other. So our laser beam is a very intense, coherent source of electromagnetic radiation. But coherent means that the particles are all in the same phase and have the same frequency. Now, a laser beam therefore has photons which have the same frequency, so therefore they'll have the same amount of energy in each photon. So if we consider the laser beam as a stream of photons, each with an energy of E equals hf, we can assume all of our photons in the laser beam are identical because we've got coherency. So therefore we can work out the values of the entire laser beam. So we can also consider the laser beam as a wave, where all of the wave is in phase with each other. So we can say that when the wave's in phase, they're constructively interfering, so therefore we have a high energy. So there's a phase difference in our wave of 0 pi radians, or we could say 2 pi radians, so no wavelengths or one complete wavelength. Now, we know that the power of a laser beam is the energy transferred per second by the photons. So we can say that the power of a beam is n times by hf, where n is the number of photons in the beam passing a point in each second. So we can only do this because we're assuming that all of the photons in the laser beam are identical to each other. Now, this value of n incorporates the concept of time into the power equation. Now, antiparticles are like mirror images of particles. A particle can be described in terms of its charge, its mass, its baryon number, its lepton number, and its strangeness. Now, antiparticles have the same rest mass but completely opposite all other properties. Now, the notation for a particle and its antiparticle are using the hat symbol. So if the particle is x, the antiparticle is x hat. Now, the first antiparticles were scientifically observed in the 1920s. Now, most antiparticles go by the name of anti before for the actual particle, such as the antiproton. The only exception to this is the antiparticle of the electron, which is called the positron. So as we can see here, that particles and antiparticles have the same rest mass but have completely opposite values in all other properties. So whilst they have the same rest mass and same rest energy, every other particle property is reversed for an antiparticle. So this includes charge, baryon number, lepton number, and strangeness. Now Einstein had shown that the mass of a particle increases the faster it travels. So E equals mc squared relates the energy supplied to the particle to its increase in mass. So when the particle isn't moving, it has a rest mass, which is the minimum mass possible. But when the particle is moving, it has a larger mass, which we call the relativistic mass, which is the rest mass plus an extra amount of mass. So this indicates to us a fundamental link between the energy store of an object and its mass. Now, Einstein indicated that the rest mass of a particle corresponds to the rest energy of the particle. So the rest energy must be conserved in the conservation of energy, and this effect is very noticeable on the scale of particles. Now, as Einstein postulated that the mass of a particle when it's stationary, its rest mass, corresponds to its rest energy locked up in mass, we can say that the rest energy mass must always be conserved in all decays. Now, Paul Dirac predicted that the existence of antimatter, which could unlock rest energy, so whenever a particle and a corresponding antiparticle met, they would annihilate and release this energy into the universe. So it's been realised that on a quantum scale, the scale smaller than subatomic particles, there's a constant flow between annihilation and pair production. So at the quantum level, matter and energy are interchanged between each other, because as humans we're oblivious to this process as it happens on a scale much smaller than our senses can detect. So the constant cycling between the forms of energy and matter on a quantum scale can also be known as the quantum foam. Now, the processes of annihilation and pair production have profound consequences on the composition of the universe. So antimatter and matter can carry out two processes. The first process is annihilation. So when a particle meets its antiparticle, the two are attracted to each other due to having opposite charges. So they'll proceed to annihilate. So they'll turn all their matter into energy. So this is observed as two photons. Now, there are two photons since the momentum has to be conserved. Beforehand the momentum is zero, afterwards the momentum has to be zero, which happens because the two particles are moving in opposite directions. So a zero momentum can't be achieved with only one photon, you need two. Now the total energy afterwards must be 2hf, because each photon has an energy of hf, so we can therefore say that the energy of each particle is E0. Now we can actually observe this event, by the way, in a positron emission tachometry hospital scanner, a PET scanner. So a positron emitting isotope is administered to the patient, so this isotope releases positrons. The positrons travel a few millimeters, and then annihilate. The two gamma photons are emitted and detected by the scanners, and this allows the scanner to build up an interior image of the body. So what we can say is that the energy before is 2E0, the energy afterwards is 2hf, so therefore 2E equals 2hf, so therefore E0, the minimum energy of each photon, is equal to hf. So this is true because two photons are produced. Now the opposite of annihilation is pair production. That's when matter is created from energy, so it creates a pair of particles, the conventional particle and its antimatter particle. So the photon itself must have enough energy to form the rest mass of both particles. So they must contain enough energy to form the equivalent rest mass of both the particle and the antiparticle. Now because the photon has an energy of hf and the particle and antiparticle have an energy each of E0, we can therefore say hf equals 2E0, so therefore we can say that hf equals 2E0. Now any extra energy above this is found as the kinetic energy in the particles. So this is an important idea, because if the photon doesn't have enough energy to produce the rest energies of the particle and antiparticle, the process simply doesn't take place. That's why it's extremely rare for very massive particles to be produced in this process. So let's take the electron for example. It's got a rest energy energy of 0.511 MeV. Therefore, for pair production, an electron and positron must form from the photon. So therefore, the minimum energy the photon must have is twice the energy of the part of the electron, which is 1.022 MeV, which is 1.64 times 10 to the minus 13 joules. So a photon with less energy couldn't create a positron and an electron. Now, as it's important to note that the photon will always need a little bit more energy than the minimum, because this gives the particle and antiparticle enough kinetic energy to overcome their attraction to each other and just annihilate themselves as well. So that's very, very important. That's actually slightly bigger than the minimum energy required. So it's important to note that if the particles just have their rest mass, the particle-antiparticle will annihilate, but if you wish them to have a little bit more, they'll have enough kinetic energy to get away from each other. So the difference in pair production and annihilation has the following effect. The annihilation of a particle-antiparticle can lead to pair production. Then each photon then produces its own particle-antiparticle. So each photon will then have its own set of particle-antiparticles. So this means that the resultant particles and antiparticles have a smaller mass than the previous particles, as the starting energy is now spread between two photons. Again, these particles, antiparticles, will carry out annihilation. However, the photons produced will have half the energy of the previous photons produced in the last step. So this means that with repeated annihilation, pair production, the energy becomes spread out over the universe and the possible particles produced are less massive. So this is the reason why energy gets dissipated throughout the universe, and the most common particles in the universe are the ones with the least mass, which is the concept of entropy. Now we can compare and contrast the processes with the following table. In annihilation, you start with a particle-antiparticle, you finish with two photons, so the minimum energy calculation is E0 equals hf. Whilst in pair production, you start with one photon and finish with a particle-antiparticle, so the minimum energy calculation is 2E0 equals hf. Let's now have a look at particle interactions. So there are four fundamental interactions in nature. You've got gravity, which is the weakest interaction in the universe. Then you've got the weak nuclear interaction. You've then got the electromagnetic interaction. And then you've got the strong nuclear interaction, which only works on hadrons. So we can sum up the properties of the different interactions with the following table. Now it's important to note that the strength is how strong the interactions are compared to each other, and the range is how far reaching the interaction is. Now you've got to be able to remember that the different properties of the different types of interactions for your exams. Now it's important to note that an interaction is produced by an exchange of bosons between objects in the universe. So this is a fundamental interaction which produces the macroscopic idea of a force. So here the exchange particles are moving between the magnets, and this produces the electromagnetic interaction between the forces between the magnets that we observe on the everyday level. Now the particles that work here as exchange particles are referred to as virtual particles, since they can only exist for a short amount of time, because the energy needed to produce them is borrowed from the universe. Now Heisenberg's uncertainty principle states that pretty much that the bigger the energy needs to be borrowed, the shorter the time it can exist for. So what this means is the larger the exchange particle, the more energy is needed to be borrowed from the universe, the shorter the time it can exist, so the shorter its range and therefore the size of the field. So if the exchange particle is massless, it requires no energy to be borrowed, so therefore it can exist forever, so its range and the field it produces are infinite. Whilst, like we said before, the larger the mass of the exchange particle, the shorter the time it can exist, the shorter the range of the force it produces. Now, these particles are also referred to as virtual particles because they can only exist for a short amount of time. And in addition to that, if the particle was observed by an experimenter, it would no longer produce a force and would cease to exist, so we can never observe these exchange particles directly. We can only ever observe the effects of the exchange particles. So it was discovered that forces occur in the universe due to the exchange of bosons, or virtual particles, which can also be called exchange particles. So these particles are virtual, as they can't be detected directly, and if we intercepted them we would stop the force acting, so the property of the virtual particle determines the properties of the force. So objects in our universe exert forces on other bodies as they exchange virtual particles, or bosons. So the properties of the exchange particles lead to the properties of the force itself. Now, the exchange particles cannot be observed directly, and the exchange particles transfer energy and momentum between the objects. So virtual particles work a bit like two people on roller skates throwing things to each other. So if person A throws a bowling ball to person B, A slides back when they release it and B moves back when they catch it. So repeatedly throwing the ball backwards and forwards between A and B causes repulsion between the two. So this is the act of exchanging an exchange particle between a repulsive force or interaction. And again, remember that energy and momentum are being exchanged between the two bodies. As you can see here, that is acting to produce a repulsive force. Now imagine the two people on ice skates representing the two bodies, okay, are exchanging a boomerang. So when person A throws it, it pushes them towards B, and when person B catches it, it moves them towards A. So this is like the exchange particle causing an attraction. So the act of exchanging the particle here has caused an attractive force. So again here, energy and momentum are being exchanged between the objects. So just to clarify, in the standard model of particle physics, there are a number of different types of exchange particles. You've got photons, which carry the electromagnetic interaction, W and Z bosons, which carry the weak nuclear interaction, and gluons or pions, which carry the strong nuclear interaction. Now, we haven't yet discovered the exchange particle for the graviton, for gravity, due to its weak nature. However, we do believe it could exist, and it could be called the graviton. So let's just have a look at our different properties. So we've got the graviton, which is the exchange particle for gravitation. This is an exchange particle that's never been observed. You've got the photon, which is the exchange particle for electromagnetism. This particle has no mass, so has an infinite range. So this means that the electromagnetic force has an infinite range. You've got the gluon, which is the exchange particle for the strong interaction. This is a massive particle, so it can only exist for a short amount of time, so therefore the short interaction has a short range. So that, as we mentioned before, it limits how much the strong interaction can act on things. And you've got the W and Z bosons, which are the exchange particles for the weak interaction. Now there are three bosons for the weak force for a really complicated reason. It's to allow the quantum isospin and hypercharge to be conserved in decays. Now the W boson is the largest exchange particle, so has the shortest range, as it exists for the shortest time. So this means the weak force has a very, very short range. Now when exchange particles are exchanged between particles, it can cause the particles to change type. So Richard Feynman soon realised that the general public didn't understand how this works, so he produced diagrams to make this more understandable, which he called the Feynman diagram. So these are diagrams used to describe and show particle interactions and decays caused by exchange particles. So like we said before, the exchange of an exchange particle can lead to a particle change in type. Now it should be noted that the axes aren't really shown on Feynman diagrams, but they can show time and distance, and it is actually more conventional to depict antiparticles as normal particles with the arrow of time reversed. So a Feynman diagram can show how two particles interact and change over time in the universe. Now please understand, it's not a graph, it's a diagram to help people understand what's going on in the particle level. So in our previous understanding, we would have said that a force was causing a particle decay, like beta decay. Now here what we can do is we can look at the actual interaction taking place in certain situations. So for example, we've got the past, which is the particles before the interactions take place. Now we tend to show particles as straight lines on diagrams. We've got the present, which is when the exchange particle is exchanged, causing the interaction. Now we show exchange particles as wiggly lines on the diagram. And we've got the future, which is the particles produced by the interaction. Now we've got some rules for Feynman diagrams. Time goes vertically up on the diagram and space goes horizontally along the diagram. Particles are shown by normal arrowheads and antiparticles by reversed arrowheads. If the particle is stationary, you draw a vertical line. If the particles are moving, you draw a slanted line. When a decay occurs and a boson causes an interaction, a wavy line is drawn between the particle and is labelled with the exchange particle, and the particles produced afterwards are then drawn as a label line. The baryons stay on one side of the diagram and the leptons on the other side, and the W bosons carry charge from one side of the diagram to the other side, and you've got to make sure the charge is balanced. So here's an example of a Feynman diagram. Baryons are drawn on the left hand side and leptons are drawn on the right hand side. Now here the boson is transferring negative charge across the other side, so therefore all of our charges balance. Now one aspect students struggle with for Feynman diagrams is working out which exchange particle to use. So to work out which exchange particle or boson to use in each interaction, look at the following rules. If the interaction is that it causes attraction or repulsion between particles, the interaction is electromagnetism and the exchange particle is the photon. If the interaction is between hadrons and there's no leptons produced, the force is due to the strong interaction and the exchange particle is a gluon or a pion. And if the interaction includes leptons and the particle changes type, their interaction is the weak, so therefore the exchange particle is the W plus or the W minus or the Z. Now let's see if we can work out which W to use in the weak interaction. So if you start off with a positive and it becomes neutral, you can think of the particle thrown away its positive charge, so the boson will be positive. If the particle starts off as negative and then becomes neutral due to the interaction, you can think of it as throwing away its negative charge, so the boson will be negative, so it'll be the W minus. And if it's neutral and becomes positive, it's like it's losing a negative, so the boson is a negative, so it's W minus. If you start off with a neutral particle and it becomes negative, you can think of the particle as losing its positive charge, so the boson, the W, is a positive one. So let's have a look at an example of a Feynman diagram. Remember that these diagrams are showing how the particles change over time due to interactions by exchanging an exchange particle. So here you've got two baryons, so therefore it's the strong interactions. The exchange particle is the pion because there's no particles changing type and there's no leptons present. Here it's due to electromagnetic repulsion, so our exchange particle is the photon. Here a neutron is decaying due to the weak interaction, so it's changing, and there's also leptons present, electrons and anti-electron neutrinos, and also it must be the W plus because it's gaining a positive charge because it starts as neutral and becomes a positive, so therefore it's the W minus because it's gaining a positive charge, so it's throwing away its negativity. Here the proton decays to the neutron, so a positron and an electron neutrino are produced, so you've got a decay and you've got leptons produced, so therefore it's a weak interaction, and as it's starting off as a positive and it's becoming a neutral particle, the proton to the neutron, it's losing its positivity, so it's throwing away its positive charge, so it must be the W plus boson. Now it's important to note that most processes that have nuclear decay occur via the weak interaction. Now what's happening here in this nuclear decay is the W boson has passed from an unstable nuclei into its stable products. So this decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. Now the only exception to this is alpha decay, which doesn't involve leptons or particles changing type, so it must be a decay via the strong interaction. So because it's the strong interaction, the alpha decay is a lot faster. Now in the previous example we just considered a radioactive or unstable nucleus to be an unhappy face. In reality it's more appropriate to say that it's like a bubbling volcano. It's constantly churning and turning, waiting to erupt and emit a form of radiation. But what causes instability and what interactions are found in the nucleus? So there are two interactions which affect the stability of the nucleus. The strong interaction, which is attraction between all the nucleons, and the electromagnetic interaction, which causes repulsion between the neutrons. So like we said before, a stable nucleus is where the strong interaction is much larger than electromagnetic, whilst nuclear stability is where the strong interaction and the electromagnetic interaction are of similar size. So a radioactive nucleus will move towards the stable or ground state by radioactively decaying and producing energy or particles, and this energy will be distributed over a larger number of quantum states. So it can happen by either alpha, beta or gamma decay. In reality there are two types of beta decay, and there's also a fourth decay process that can occur called internal conversion. So alpha decay is when two protons and two neutrons are lost from a nucleus. So the atomic number goes down by 2 and the atomic mass number decreases by 4. So the new element is formed 2 places lower in the periodic table than the original element. So alpha emission is when an alpha particle or helium nucleus is ejected from the parent nucleus. Now you've got a new element formed because we've lost 2 protons. Now whilst this is the same as a helium nucleus, the term alpha is used if this alpha particle has originated from the nucleus. So this is an example of transmutation as a new element is formed, which is formed 2 places lower on the periodic table than the parent element. Now each alpha particle is released with the same kinetic energy as there are no other products produced in the decay, as you can see in this particular animation. Now in beta minus decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus and the electron leaves the atom as a high energy beta particle. So the atomic mass number stays the same, yet the atomic number increases by 1. So we can see here that the process can produce a new element one place higher in the periodic table. So you can see that you lose 1 neutron and gain 1 proton in beta minus emission. Now beta minus emitters are found naturally in the universe but can also be manufactured by bombarding stable isotopes with neutrons. Now the new element produced in beta minus decay is found because of we've gained 1 proton. Now whilst this beta minus particle is the same as an electron, we use the term beta when the electron originates from the nucleus. Now beta minus emission is an example of transmutation as a new element is formed, and this element is found one place higher in the periodic table compared to the parent nucleus. So that's a very important idea, and you can show it here in this particular demonstration. Now, beta plus emission is when a proton is transformed into a neutron and a positron. It's the opposite decay process to the beta minus emission. So in beta plus, you lose 1 proton and gain 1 neutron. Again, we've got a new element because there are a different number of protons. And again, whilst this beta plus is going to be the same as a positron, the term beta plus is used if the particle has originated from the nucleus. It's an example of transmutation because you've lost 1 proton. As you've got a different number of protons, and this new element is found one place lower on the periodic table compared to the parent nucleus. Now, beta plus emitters aren't normally found in the universe, but they're manufactured if you bombard stable isotopes with protons. Now, gamma decay is there's no change in the makeup of the neutron, it just loses energy in the form of photons. So alpha emission is often followed by gamma ray emission. So the daughter nuclei can be left in an excited state after alpha emissions taking place, and at some point they'll fall to their ground state emitting a gamma photon. So there's no nucleon change, just a change of energy. So it's not an example of transmutation as no new element is formed. Now, a nucleus which has excess energy before gamma decay is in what we call a metastable state. So here we've got a demonstration of gamma ray emission. Now, gamma ray emission can really only occur after alpha emission. Now, when you have looking at alpha and beta decay in a bit more detail, you'll notice that there's an issue with the amount of energy produced in the decay process. Because with alpha decay, each alpha particle is produced with the same rest energy and the same kinetic energy. So all alpha particles travel at the same speed. They obey the conservation of energy mass. And with gamma decay, your gamma photons are produced with a known amount of kinetic energy, so we're conserving energy and mass. But with beta decay, some beta particles had more kinetic energy than others, so there was a variation of energies that the beta particles possessed, which seemed to violate the conservation of energy mass. So what was happening? Well, a physicist called Wolfgang Pauli suggests that the lost energy was carried away by a new particle, so that the total energy of any beta decay is constant. Now, this particle must be chargeless and have virtually no rest mass. So this was the idea of the neutrino. Now, the rest mass of a neutrino is much smaller than the rest mass of an electron. So Pauli realized that the total energy before decay equaled the total energy after the decay if you consider the energy of the neutrino which was also produced. Because if we didn't consider the neutrino, that the total energies don't equal each other, so therefore we have the beta decay problem. So the neutrino energy comes from some of the kinetic energy of the beta. So what this means is the larger the neutrino, the slower the beta particle, because the neutrino is taking some of the energy away from the beta particle. So this allowed for the conservation of energy, but Pauli also realized that the neutrino produced for a lepton is actually an anti-neutrino to conserve something called the lepton number. Now, our neutrino is pretty much another type of lepton, and there are many different neutrinos associated with the 3 different types. So if you've got an electron and an electron neutrino, a muon and a muon neutrino, and a tau neutrino. Now, as a neutrino has always been observed when a lepton is produced. So physicists have said that the lepton is like the dog, and the neutrino is like the flea. So whenever there's a dog, there's always a flea. Whenever there's a lepton, there's always a neutrino. neutrino. So when we now look at beta minus emission, you also produce an antineutrino with your electron, which means that the electron is produced with a variety of kinetic energies. Now the neutrino produced must be an antineutrino to conserve what we call lepton numbers. And in beta plus emission, the beta particles are emitted with a variety of kinetic energies because a neutrino was also produced. Now the neutrino produced must be a standard neutrino due to the conservation of the lepton number. Now, in addition to the traditional decays of the nucleus, there's a fourth nuclear decay, internal conversion. Internal conversion is a process in which a nucleus in an excited state can release its excess energy. So in internal conversion, all of the excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force, and the orbital electron is then emitted and ejected from the atom. Now, both internal conversion and beta decay eject electrons from the nucleus, but there are differences. Beta decays occurs via the weak interaction and internal conversion via the electromagnetic. Beta decays can also produce neutrinos and antineutrinos. Beta decays produce a nucleus of a new element, internal conversion does not. And in beta decay, the electrons are emitted with a range of energies, and internal conversion, all the electrons have the same energy. And finally, in beta decays, the electron is emitted from the nucleus, and in internal conversion, the electron is emitted from the shell. Let's now have a look at the classification of particles. Now, in GCSE physics, you understood that there were protons, electrons and neutrons. However, in 1932, that James Chadwick, when he discovered the neutron, that completed our particle zoo from GCSE physics. Now, unfortunately, from our previous work, we realised that particles can be differentiated via their rest mass, charge, and specific charge. But in 1936, Carl Anderson experimentally found the antimatter postulated by Paul Dirac. So this led to the idea of antiparticles, and the number of particles in our particle zoo seemed to double. Now, like we said, particles and antiparticles have the same rest mass and rest energy, but opposite properties for everything else. Now, if they were the only subatomic particles to exist, our particle zoo would be very small. Now, what happened in 1963 is that when we looked through cosmic rays, we realised that there were lots and lots of different particles, which we called exotic particles. Now, these exotic particles have a much higher mass than the proton, neutron and electron, so therefore they have a high rest energy and will produce in high energy events. Now, over time, these exotic particles decay into smaller ones. Now, the total overall energy and mass does not change. It means that the mass of exotic particles turn to many smaller, less massive particles. So we've now realised that the particles we knew about as the common particles on Earth were the smallest stable possible particles to be made, and in fact in our universe there are many more under high energy events such as supernova. You can get many larger particles possible than the smaller stable less massive particles found on Earth. So at the Large Hadron Collider we simulate these high energy events and produce these larger particles to observe them. So in reality there are many different particles and antiparticles possible in the universe. So like a zoo of animals, there are a zoo of particles. So we need to order the particles into different groups or families according to their properties. And we did this by placing particles into different families from their lepton and baryon numbers. So here's an overview of what we call the particle zoo. Now there are two main areas or two main categories of the particle zoo. The fundamental particles, which can't be broken down any further, and hadrons, which are not fundamental particles and are made of quarks. They can be unstable and can decay into other particles. Now all fundamental particles can't be broken down any further. Now all non-fundamental matter has a structure inside of it, so all non-fundamental particles are unstable apart from a few select examples. The proton is a stable hadron. The pion is a stable hadron. Now we can further subdivide this idea of fundamental and non-fundamental matter into different groups. So for our fundamental matter we've got leptons and we've got exchange particles. For hadrons we've got mesons, which are 2 quarks, 1 quark, 1 antiquark, and baryons, 3 quarks. Now your fundamental particles are stable and don't wish to decay, and your hadrons are not stable and can decay further. Now the only baryon that doesn't decay is the proton, as it's the most stable because it has the lowest baryonic mass. Now only hadrons will be subject to the strong interaction, and the fundamental particles are organised according to their properties, and the non-fundamental particles are organised to their properties, which is caused by their quark structure. So leptons, there are three types of leptons, electron, tau and muon, and each accompanying lepton particle has a neutrino which has no charge. Each lepton has a lepton number of +1 or -1. Now fundamentally the only difference between leptons are their rest energies. Electrons are the most common leptons as they have the smallest rest energy, and taus are the least common electrons as they have the largest rest energy. So a muon is a particle that decays into an electron, a tau is a particle that decays into electrons, and they both do this by shedding excess mass as energy. Now hadrons come in two types, baryons and mesons. They're both made from quarks, a baryon 3 quarks, a meson 1 quark 1 antiquark. So an antimeson is just a meson. Now they're much larger than leptons, they're unstable, but all baryons will eventually decay into protons, and only baryons can have a non-zero baryon number. So mesons equals 0, baryon 1, antibaryon -1. Now baryons and mesons can decay as they're made from quarks. When hadrons decay, the quarks change type. Hadrons that wish to decay can decay into smaller hadrons. Now the protons can't decay as they're the smallest hadron, as they're made from the smallest, most stable configuration of quarks. As a meson is a quark-antiquark pair, antimesons do not exist. The antimeson would just be like swapping the quark and antiquark around, so the meson is its own antimeson. Now a meson, which has a non-zero strangeness, is called a kaon. Now kaons are always produced in pairs, and kaons can decay into pions. Now, exchange particles or bosons carry all the forces of the universe. The range of the force depends upon the range of the boson. The mechanism of the force directly relates to the properties of the boson. Now, bosons have a 0 lepton number and a 0 baryon number. Now, we can summarize the particle zoo properties with our following table. Now, as expected, you should be able to recognize the particle the family belongs to from its baryon number and its lepton number. Now, you can tell the difference between mesons and bosons as you've got to memorize the different bosons. Now, let's have a consideration of quarks and antiquarks. To provide an underlying principle to the particle zoo, Murray-Gell-Mann proposed the quark theory, that all hadrons are made from smaller particles called quarks, baryons 3 quarks, antibaryons 3 antiquarks, mesons 1 quark 1 antiquark, and quarks cannot exist in isolation, so we currently believe quarks to be fundamental. So Gell-Mann proposed that baryons are made from 3 quarks. Each quark possesses a fractional baryon number, charge and lepton number. These then add to form the overall baryon number, charge and lepton number of a baryon. Now a baryon can only have an integer baryon number, charge and lepton. There's only certain combinations of quarks that can combine to make a baryon. Now it's important to note the same for antibaryons, and the force holding the quarks together is the strong interaction, so gluons are constantly being exchanged between the quarks to produce this. Now Gell-Mann originally named the quark after the sound made by ducks. Now Gell-Mann was inspired by the quark in James Joyce's book The Finnegan's Wake because he believed there were 3 quarks. Now Gell-Mann proposed that mesons are made of 1 quark, 1 antiquark, and that he also proposed that again they were being held together by the strong interaction. Now it's important to note that quarks cannot exist by themselves. They exist in either 2s or 3s because quarks tend to the most stable configurations. They exist in either pairs or triples. So that's a very important idea, that quarks cannot exist as single quarks, which is called quark confinement. Now there are actually 6 quarks in the universe. Now each type is called a quark flavor. You've got the up quark, the down quark, the strange quark. Now the strange quark gives a particle its strangeness, the charmed quark, and the top quark. Now this is the largest quark and therefore the most unstable, so it's actually the rarest quark in the universe, and it was only actually first observed in 1995. And finally we've got the bottom quark as well. Now Gell-Mann proposed that these quarks along with the leptons and bosons produce everything in the universe, which is what he called the standard model. So our quarks come in 3 different pairs which have contrasting properties, which he called generations. So you've got up and down, the first generation, strange and charmed, the second generation, and top and bottom, the third generation. Now the higher the generation, the more the mass of the quark. This means it's less likely for the quark to exist. This means that first generation quarks are more common than those of third generation quarks, which is why protons and neutrons are made from first generation quarks. So that's a very, very important idea. So this is our standard model of matter. So we've got our 6 quarks up and down, strange and charmed, top and bottom here. So our quarks, the 6 different quarks that combine to form mesons and baryons. Now only quarks experience a strong interaction, and any particle made from a quark is referred to as a hadron, and quarks can never exist in isolation. Now only baryons have a non-zero baryon number, and there's also antiquarks found in the antimatter standard model. Now again, antimatter has the same rest mass as matter but the opposite other properties. You've then got leptons, which are electrons, muons, taus and neutrinos. Leptons do not experience a strong interaction, and they only experience the weak and the electromagnetic interaction if they are charged. They can have a non-zero lepton number, and we've got antileptons found in the antimatter standard model. Now again, antimatter has the same rest mass but opposite other properties of the particle components. You've got your exchange particles, which mediate a force, energy and momentum in the universe, and the properties of the exchange particle lead to the properties of the force interaction. Now these particles are referred to as virtual particles since they only exist for brief amounts of time and can never be observed directly. Now we observe quarks by firing our electrons at neutrons and protons and realizing they were scattered at large angles, which indicates that neutrons and protons were not of uniform density but had a point-like charge inside of them, the quarks, which is very similar in experimentation to Rutherford scattering, except it was carried on a much smaller size. So it showed that this scattering meant that there was an internal structure to the protons and neutrons. So we've got our baryons of 3 quarks, our antibaryons of 3 antiquarks, and our mesons are 1 quark, 1 antiquark. So our baryon is a proton, which is up, up, down. Another baryon is a neutron, which is down, up, down. The antibaryons could be 3 antiquarks, and a meson could be 1 quark, 1 antiquark. And you can work out the particle family from the quark composition. So here's our proton. Here's our neutron. Now when you change your baryons, like from a proton to a neutron, what is happening is 1 quark is changing flavour, and the force responsible for this is the weak interaction. So we're changing our quark's character. So only the weak interaction can change a quark's character. So we observe change in a quark's character as a particle change in type. So the exchange of a W and Z boson causes a quark to change character. That's very, very important, as shown here in the opposite way round. Now again, you can work out your antiparticles from the opposite structure of your normal particle, and you can deduce the structure of a meson from its properties. So you must work out the charge of a meson to work out what possible quark antiquark could sum together to that charge. If the meson contains either a strange or an anti-strange quark, it's a kaon, and the only meson which can have strangers is a kaon. Now other mesons like the pion cannot contain a strange quark, only the other quarks. So you can deduce them from the information given to you in your data book. Now again, please remember the quark properties should all add up to give the overall properties of the particle. So here's an example of us doing that. So the properties of the up and the down add together to give the properties of the proton. Again, is shown here. So finally, let's now have a look at the application of the conservation laws. So it's been observed that exotic heavier particles will over time change into lighter, more stable particles. So this process is called the particle decay, and it's caused by an exchange of an exchange particle. It's similar to nuclear decays, but particles are changing from one type to another. So particle decays occur as they want to exist as low energy, more stable particles. So the heavier particles don't have to decay back into the more stable products that produce them if we produce them from our more stable particles by get them in high energy situations, because there are many different decay pathways based on probabilities. So particle physicists can examine the different particle decays and use this to understand how the fundamental forces work. So for a particle decay to occur in the universe, the following quantities need to be conserved between the particles before and after the decay. You've got the same total energy mass before and after, the total momentum before and after, the total charge before and after, the total baryon number before and after, and the total lepton number before and after. If all of these properties are conserved in the decay, then the decay is observed in the universe. If a property is not conserved, we say the decay does not occur due to a violation of that property. So the decay doesn't occur due to a lepton number violation. Now at A level, you must be aware that energy mass and momentum need to be conserved, but you don't need to calculate them. But you do need to prove that charge, baryon number and lepton number are conserved in a particle decay. So what you will do is, if you're given a decay in an examination, you've got to check if the decay occurs by drawing a property table. So you look at the charge. Now the row has to be the same before and after to conserve charge. The row has to be the same before and after to conserve lepton number. And this row has to be the same before and after to conserve baryon number. So all rows must be conserved for a decay to take place. So you'll see here that you can work out your overall charge, lepton number and baryon number before and afterwards, and see that if they're conserved, that the decay will take place. Now you need to recognise what a family of particle belongs to and deduce its properties based on that, which does take practice. Now you can abbreviate your properties in your table as shown. Now when all values are conserved, a particle decay occurs in the universe. Now, there were several issues with our laws of particle decays. When we analysed the conservation laws with the particle decays that occur in the universe, there were some decays that should happen and could happen, but don't happen and we never observe them. So there must be another quantity which needs to be conserved in a particle decay. So our laws of physics were incomplete. And in addition, certain particles like kaons were created easily in particle collisions yet decayed much more slowly than expected for their large masses. So they should be decayed by the strong interaction, but instead were decaying by the weak interaction. So another quantity must be causing this. So our laws of physics were incomplete. So how do we solve this? To explain these problems away, we came up with a new particle property called strangeness. Now strangeness was postulated to be conserved in any interaction with a strong, but doesn't need to be conserved in the weak interaction. It's literally strange. So this explains why certain decays didn't occur, they didn't conserve strangeness, and this explains why certain decays took a long time to occur. They conserve strangeness, so the decay can only occur, they don't conserve strangeness, so it can only decay via the weak interaction. Now some physicists do believe strangeness to be a fudge on the particle model due to a lack of fundamental understanding. So what do we say? That particles which have a strangeness property all decay through the weak interaction. They decay into pions, which are referred to as kaons. That they don't decay into pions which have different rest masses, which are greater than the proton's rest mass, and decay into protons and pions, and they must be created in pairs. Now in our modern understanding, strangeness is conserved during the strong and the electromagnetic interactions, but not during the weak interactions. So this is why this means that the lightest strange particle kaons can't decay by the strong interaction and must decay instead by the much slower weak interaction. Now in most cases these decays change the value of strangeness by about 1. So this is why kaons are easy to produce but are difficult to decay into other particles. They can be produced via the strong interaction but only decay via the weak. However, this doesn't necessarily hold in second order weak reactions where there are mixtures of different K mesons, but all in all the amount of strangeness can change in the weak interaction by +1, 0 or -1. So Gell-Mann solved the kaon problem in physics by inventing a new particle property for all particles, strangeness. So it must be conserved in the strong interaction but can change by +1 or -1 in the weak interaction. Now originally this was a bookkeeping device to help explain patterns. However, over the next few years we discovered that baryons and mesons are made from quarks, and one quark was causing all this strange behaviour, so we called it the strange quark. So the weak force causes quarks to change type, and it can cause a strange quark to turn to a different type of quark, that therefore strangeness is not conserved. However, still to this day we don't really know why the strange quark is strange compared to all the other quarks. We don't have a fundamental understanding of what strangeness is. So just to clarify, strangeness is always conserved in strong interactions. It can change by 0, +1 and -1 in the weak interactions. So the strange number can change by +1 and -1 via the weak interaction only. If the strange number changes by more than +1 and -1, it does not happen. And then finally, if the strangest number is conserved, the decay can happen either via the weak or the strong interaction. Now in previous lessons we've used particle Feynman diagrams, but you can also express these Feynman diagrams with quark structures as well as the particle structure. So looking at the particle decays in terms of quarks and leptons is a fundamental way of considering the situation. Now you only have to bold the quarks which change in the decay process. So in the beta decay process, the down quark can change into an up quark, and on the particle level it appears the neutron turns into a proton. Now, the weak force is exchanged between the quarks underneath the particle level. So a true Feynman diagram should be on the quark level, since this is where the exchange particles operate. Now, you can see here that you can observe your different quarks changing in your Feynman diagram. Now you could be able to state the quark Feynman diagrams for both beta minus and beta plus decay, as you can see in these particular diagrams. Now it's noted that with beta minus decay, again, it only occurs in free neutrons. As it's becoming positively charged, so as it's thrown away it's negative, it's a W minus boson, which is the exchange particle. Whilst with beta plus decay, it occurs in protons in the nucleus as it's becoming neutrally charged, so it's the W plus boson, which is the exchange particle. Now again, you can show in your conservation diagrams the quarks that are changing character and the leptons in the decay. Now as time goes on, we continue to develop our understanding of particle physics. Now new theories are created to explain observations from experiments. Now physicists can hypothesize new particles and the properties they should have, and experiments then carried out to observe these particles and their properties. Now to carry out investigations in particle physics, physicists need to work in large groups to do this. This is because particle accelerators are expensive and so are difficult to construct without a large amount of funding. It's again because working in large groups allows the various different skills and talents to be pooled together to help explain observations. It's because particle physics experiments produce lots of data which can only be analysed quickly when many physicists work on them, and it's because working in large groups allows work to be checked and peer reviewed very quickly. So let's summarise what we've looked at in this particular revision session. We've looked at the simple model of the atom, the atomic mass unit, the charge and mass of the proton, neutron and electron in SI units, the specific charge of the proton and the electron. We've looked at the idea of the notation of used in nucleons as well. We looked at the strong nuclear force, its role in keeping the nucleus stable, it's a strong range attraction up to about 3 femtometers and a very short range repulsion closer than 0.5 femtometers. We've looked at the photon model of the atom with E equals hf equals hc over lambda. We've looked at that for each type of particle. There's a corresponding antiparticle. We've compared particle and antiparticle masses, charge and rest mass. We show that there's a positron, antiproton, antineutron and antineutrinos as antiparticles. Have knowledge of annihilation and pair production and the energies involved. We know that there are 4 fundamental interactions: gravity, electromagnetic, weak and strong nuclear. That there's the concept of the exchange particles, knowledge of the gluon, the Z and the graviton won't be actually needed for this particular specification. That we know that the electromagnetic force has the virtual photon as the exchange particle, the weak interaction down limited to beta minus and beta plus decay, electron capture and electron proton collisions, W plus and W minus as the exchange particles. And then for unstable nuclei, we know what alpha and beta decay, known equations for alpha decay, beta decay and the need for the neutrino, and that the existence of the neutrino was hypothesized to account for the conservation of energy in beta decay. We know that hadrons are subject to the strong interaction. There are 2 classes of hadrons, baryons and mesons. Understand baryon number, conservation of baryons number. The proton is the only stable baryon. The pion is the exchange particle of the strong nuclear force. Kaons are particles that can decay into pions. We know about leptons as electrons, muons and neutrinos and their antiparticles. We know about lepton numbers as a quantum number and the conservation of the lepton number for muon and electron leptons. That muon acts as a particle that decays into electrons. We know properties of quarks and antiquarks, their charge, their baryon number and their strangeness. Combinations of quarks and antiquarks are required for baryons, antibaryons and mesons, and the decay of the neutrons should be known. And we have applications of the conservation law for charge, baryon number, lepton number, strangeness to particle interactions, and then you should recognise that energy and momentum are also conserved. And finally, we've got strange particles. That strange particles are particles that are produced through the strong interaction and decay through the weak. Strangeness as a quantum number to reflect that strange particles are created in pairs, the conservation of strangeness and strong interactions, and that strangeness can change by 0, +1 or -1 in weak interactions. So thank you very much for watching this particular revision session on particle physics. I hope you've enjoyed this revision session and have a lovely day.